Hopefully you can see that.
Yeah, all good.
Cool, thank you. Well, welcome everyone. I'm Simon. So you may have had annoying emails from me, all kinds of tweets and things going on. We've got loads of ways of getting in contact with us, social media, website, emails, whatever. If you see us in the street, just stop us. We're usually quite easy to see, carrying telescopes. I'm the only person that carries telescopes up and down the high street in Bath. We use the little trolleys and things you take to things like Glastonbury, etc., to cart our telescopes around. So we're quite a sight when we are moving telescopes around Bath. But yes, love to have a chat. We've got 121 in our membership currently. And if you're not a member, if you just popped along, then we'd love to have you as a member. If you are just popping in tonight, for an adult visitor, it's £5. If you're a student, it's £2.50. And if you're in full-time education under 16 or under, then it's free. Okay, so if you do owe a little bit of money, then just come and see me afterwards and we can just settle up. The usual though, this is an old house. It's wonderful that the Herschels lived here. They weren't too great on fire safety, which means that if the alarm does go off, that door, glazed door behind you is actually open and allow you to go into the garden in the event that the one exit route we have, which is up the wooden staircase, is blocked by fire. Okay, so if that's not available, then please go out there. We'll congregate at the back of the garden and we'll watch the house burn down and all the history inside it. Maybe not, but yeah, but as long as you're safe. So that door is safe, so is open. If you've got a chair in front of it, you just move your chair out as you're sort of exiting the building, just to make it clear for the people behind you. Okay, we do have a toilet at the bottom of the stairs. Anything else on health and safety? No, I've never actually even heard the alarm in here. But let's crack on. So what have we been up to? Well, we've been up to terrible weather. I showed a slide last time we met in February of all the cancelled events that we had in February. Similar position in March on our outreach and also getting together as a club. I think every single one of our club meet nights was peeing it down or fully clouded. So we haven't actually got together as a club for about 6-7 weeks, which is quite rare really, because normally it's every couple of weeks we're out observing. One day this weather will clear and we'll actually see some clear skies. It's just not yet, so fingers crossed on that one. But some people have been out and capturing all kinds of things. I think this is yours, Roger.
I can see that, yes.
Yeah.
Mm-hmm.
Very nice, Roger.
Thank you.
Is that a bit better? That's a bit better. Right, yes, this is Pons Brooks, 12P Pons Brooks. Do you want to tell us how you took it?
Well, with the telescope and the camera, that's a start.
Excellent. Oh, well, that's as good as any. Well, let's move on to the next one then.
No, that was about half an hour's total exposures just sort of blended together.
Yeah, and we've got some lovely features coming out on that tail there.
Yeah, the tail sort of separating partly at the back there.
Yeah, well done for that. I really like that one, just up there. We've got Alan's picture of the other comet. I can't pronounce it. Was it? Does anyone know what it was called? Sam or something? I can't remember.
Yeah.
But there it is, and it's in the chain of galaxies in this area. So is it Markarian's chain here? So some people have managed to get out and do some photos. We've got some Orion photos being taken. So despite another one of yours, Roger.
All right.
Despite the weather, people are actually finding the clear gaps and they are sort of getting the telescopes out and taking some really quite lovely images. A lot of people who are on the WhatsApp group as well, we've got for photography and sharing tips and ideas. And it's quite nice looking at some of these images, how people's photography is actually improving with the feedback we're getting in the WhatsApp group of, have you tried this? Have you tried this piece of software? All that kind of stuff. So if you are a budding photographer or want to start capturing, then I can really recommend getting on that WhatsApp group, because people are really sort of beginning to blossom on it. We've got Paul on the Sombrero Galaxy. We've got Mike on he's eventually got his telescopes to work. Mike's the kind of person that gets a broken telescope and fixes it. And great, and he eventually gets some really good images. So we've got, I think this is Copernicus. Yes, that's Copernicus there. So some lovely lunar images. It's just quite an adventure for him fixing the telescopes and actually getting to the point where he's able actually to image with them. He doesn't just do the optics, he does the drive trains, he does everything. So yeah, if you want to see sort of some of what looks like some of the good traditional 1980s, 1990s people making their own telescopes and mounts and things, that's Mike, but he's doing it with microelectronics and things like that. So it's really good stuff. We've been out as well. We've even got Steve again. I think I'm trying to get you in every single shot we've got. So this is up on top of the Abbey. This is last week. Yeah, it is. That's sunset last Friday. So it does get clear. Honest, it does. We've got viewing the moon there, and you can see there was a bit of cloud, so it's a bit touch and go, but it wasn't too bad. We've done 10 different sessions on top of the Abbey now since February, and it's great. We've had some new members that way, and also they share some of the revenue with us, so we get to put it into outreach and new kit that people can borrow from us. So it's sort of a win-win as well. The only downside is carting some of this 30 kilos to 50 kilos of kit from the bottom of Bath Abbey to the top, up winding staircases, without damaging yourself or the telescopes. And as everyone knows, I'm very caring. As people start slipping, go, careful of the telescope. Well, but then I've got my comeuppance. You can't see. Actually, you might see. I shut my fingers in one of the Abbey doors. So that's my comeuppance. So what else? It's not been bad. It was clear. So we've got Orion there, and actually you can see some of these small little windows in the sort of parapet here. We were actually observing Mercury through that on Friday night, which was kind of fun. It wasn't on this side, it was actually on the other side here. This is more due south. But even in the middle of Bath, despite all the light pollution, you can still give a good show, and you can take people around the night sky, and they can enjoy. They can find out that Sirius is actually there and nice and bright. And we've also been supporting here, the museum, just out there where Uranus was discovered. And this was the vernal equinox on the 20th of March, where we set the solar telescopes up and just prayed that the sun did actually appear just for a few seconds. And I understand it did for a very short period, but there was quite a lot of talking. So again, fingers crossed for extended periods of clear skies soon. And I've been out and about doing lots of stuff on outreach, using our workshops, but also the planetarium. And we had a very, very busy British Science Week. When was that? Gosh, that was 2 weeks ago, where those are the locations. We went 5 different schools over 5 days. That's Camilla and I. So I'm trying to remember all the names. We've got St. Michael's there. That's St. Patrick's. That's St. Augustine's. That's North Bradley. And that's St. Benedict's. And so we did full days in all of them. And what that meant is we saw 990 pupils that we actually gave workshops to during that week. And some of the pupils had multiple workshops, so we've not included the multiple times we saw them as well. So 990 different kids we got to see during that week. It was exhausting, but extremely rewarding. So I loved it. A reminder that we do have, I talked about, we generate revenue from going and doing stuff on the Abbey. We've got telescopes that we've got out for, if you remember, you can hire out these telescopes. So you can go onto the website. You can see if one of them's free. We've got 2 just like this, the Skywatcher SkyMaxes. We've got Cecilia and we've got Caroline. And we've got a bigger telescope, an 8-inch, which Merrick's currently got, I think, which is called Chandra. So we've got 3 that are actively used. There are other ones, but these are the good ones with go-tos and easier to use, rather than sort of some of the ones that we've been loaned, also given previously, which are just a little bit too difficult to use for a starter. So that's why we've got these ones. But yeah, just pop onto Telescope Loans on our website. If you're a member, then you can get one of these telescopes for 4 weeks, 8 weeks. Gosh, given this weather, maybe a year. I don't know. No, maybe not that long, but fingers crossed. So we did a quick whiz round. 6 photos were suggested for our membership card to replace the existing one. We've got a lovely little image of, I think that's, is it 101? Yes, it's the Pinwheel Galaxy. So we're going to replace that for all new members. So we're going to put a different card design on. So 6 people, our astrophotographers, submitted designs, and you have voted. And would you like to know who the winner is? This is the winner. It's Rogers. That's the elephant's trunk. Ooh. So we'll be getting that into card form, whizzing that. So hopefully in a few weeks' time, all the new cards will be going out with the elephant's trunk on there. So congratulations, Roger. A little round of applause. Everyone like your photo? No, speech.
No.
So what have we got coming up? We've got a series of talks. So Lee Fletcher is going to join us on Zoom in April, talking about gas giants. We've got high impact with Penny. We've got Pete Richardson talking about the 20-inch telescope that he's building. Hopefully he'll finish it in June. I've talked to his wife, and she's beginning to get exasperated, so he must be getting close to finishing the build soon. And we've got the Astronomer Royal for Scotland. Catherine Hayman is going to give us a Zoom talk in September as well. So that'll be a nice kickoff. We've got Chris Lintott, who could actually be coming to Bath to talk to us. We're going to go to Brilsey for that one. So on the 30th of October. We did have a TBA on November, but that's actually going to be the UK's reserve astronaut. That's going to be, remember, Megan Christian, who's our reserve astronaut, who's there in case Rosemary Coogan has any problems in her training that she's currently doing at ESA. Then Megan steps up to take Rosemary's place. But Rose is doing particularly well at the moment, so Megan's available to do talk. So she'll be talking to us in the 27th of November. And Merrick has very kindly offered to talk to us. Having done the members talk just in February, everyone really liked his planetary atmospheres, one that he did over about 10-15 minutes. Well, he's gonna elaborate, and he's going to fill 45 minutes to an hour. So rather than mushing through, we're going to have a full treat of going through that and a little more detail and a little more depth. So very much looking forward to that. Right, so I've whizzed through. How am I doing on time? Almost perfect on time. Dr. Emma Curtis Lake, she came to talk to us a couple of years ago, just after the launch of the James Webb Space Telescope on the 25th of December 2021. And she was like enthusing about all the wonderful things that were going to happen. And we also thought, what's it going to be like? What's it going to be like? Well, 2 years later, the newspapers, the magazines have just been full of all of that information. So we've asked Emma to come back and with her enthusiasm, take us back through what the discoveries have been, sort of some of the key things that you may have missed, some of the stuff that perhaps didn't get quite the splash of the headlines, but actually is much more interesting in terms of depth. So it's going to be the discovery of the distant universe. Emma, she is at the University of Hertfordshire. She's currently on maternity leave. She is a Webb Fellow, and so part of her job is to actually talk to people and actually educate people all about the James Webb Space Telescope. So what I'm going to do now is I'm going to hand over to Emma.
So first off, thank you so much for having me back. Yeah, it was just after the launch. We weren't sure that how good it was going to be as a telescope. We were hopeful. There were good signs. Things hadn't gone wrong, but there really wasn't anything new yet. But I was trying to say that it was going to transform this area that I work in, which is the very distant universe. And you're going to soon see what I mean by distant universe. This is the furthest that we can see in the universe. So I've got a couple of QR codes throughout. I've actually sent the clickable links to Simon if he'd be willing to forward them on if QR codes isn't something you're quick to use. There's one just for feedback, which helps me for my grant. And there's one which will take you to beautiful web images. So, I mean, I can't start a talk about JWST without enthusing a little bit about how incredible this telescope is before I actually tell you the discoveries. It's the largest telescope ever to be launched into space, with this image that I just have to show in every talk, showing the scale of it compared to the other much loved space telescope Hubble, which I used through most of my career before Webb came along. And here they are for scale. Here's a little person for scale. Do you see my pointer, by the way? I'm pointing things out, but.
Yeah, can see your pointer fine, thank you.
Thank you very much for that. So even though Webb is so much bigger than Hubble, it's actually a lot lighter than Hubble. So there's incredible engineering all the way through of the instrument. And what it's done, which is really revolutionary, is it's put a mirror into space that's bigger than the rocket that took it there. And we've now shown that it works. So you can imagine that astronomers are pretty excited about this and have a lot of wacky ideas of where we go next. There are other big telescopes planned. And the way it does this is with 18 individual mirror segments. Tilt on each and curvature could be changed independently to be able to focus it in space. And in the first 30 days, it traveled 1 million miles to second Lagrange point, a special point in space where normally if you're orbiting around the sun further away than the Earth, you would start trailing behind. But at this particular point, or orbiting around this point, the gravity from the Earth allows it to keep up. And that allows it to maintain this configuration where the mirror and the instruments which sit behind the mirror are completely shielded from the heating effects of the Earth and the sun, and allowing it to cool down to incredibly cold temperatures. So without any extra help, it was cooled down to 50 Kelvin. That's minus 223 degrees Celsius, and with a little bit of extra cooling around 39 Kelvin. And there's only one instrument on board that need further Kelvin to just further cooling to 7 Kelvin. That's minus 266 degrees Celsius. And so I believe this has been said in a documentary now. So when I give this story, people often have heard it, but there were no cameras on board. And when it was released from the rocket, it had to be folded up. It was unfolded. The way they knew that things were working is that they had switches that changed state. And when they were deploying the sun shield, which was one of the things that caused such a major delay back in 2018, is one of those switches didn't change state. So they didn't know that that sun shield had fully deployed. And the only way they could tell is by watching the temperatures plummet, and they did. And if that hadn't happened, well, if it hadn't deployed, that would have been mission over. That would have been all of the billions of pounds, dollars gone. So the reason it needs to be so cold, the reason this can't be done from the Earth, is because Webb is looking at infrared wavelengths. So if this is the whole electromagnetic spectrum, running from gamma rays have very short wavelength, X-rays, which of course we can take images of our bodies, all the way to radio waves, which are the longest wavelengths. Our eyes are sensitive just to the visible part of the spectrum, but we're also There's just one other part of this whole electromagnetic spectrum that we are sensitive to, and we feel it as heat, and that's the infrared. And it's at longer wavelengths than the visible. And this shows you how much Hubble could see. It poked a little way into the infrared. It poked a little way beyond the visible into the ultraviolet. Now, there was another space telescope, which actually I talked about last time, which I loved dearly, Spitzer Space Telescope. It did look in some of the wavelength range covered by Webb, but it was tiny compared to Webb. It was affectionately called a rubbish can in space. Like, it was about the size of those old metal rubbish cans that we had. And so even though some of the things that I'm going to tell you about that Webb can do for the distant universe, technically, if there was the sensitivity available, Spitzer might have been able to do it. But with such a small telescope, it was really not capable of it. So this has been the only thing to sort of probe this region of the electromagnetic spectrum until now at such incredible depths and sensitivities. And this telescope has been designed fully complete. It cannot be changed. So it's 1 million miles away. We can't send astronauts there to upgrade it or fix it. Hubble has had an incredible lifespan, over 30 years. There's even talk of sending further missions potentially to upgrade it if they can nudge it back out, further out of orbit, because currently it's starting to fall into the Earth. But 1 million miles away, we can't do this. So the instruments that it has, we are stuck with. This is everything we're going to have. And there are just 4 instruments. They're housed on the back of the mirror. Very safe in there, no micrometeoroid impacts, very well protected. And we just have these 4 instruments. I like this infographic because it shows you their capabilities. So if there's a camera symbol, it could take imaging. If there's a prism here that's splitting up the light, it can take spectroscopy. This little star with something blocking it is for a chronograph. So when you're blocking the light of a central bright object, which is usually a star, you can see very faint features around it. So whether that be a protoplanetary disk or exoplanets or something like this. So our first instrument here, NIRCam, it's a near infrared camera and was built in Arizona. And the interesting thing about NIRCam is that was what was used to focus that huge mirror. 18 individual mirrors had to be adjusted to make that whole thing work as a single mirror. And if this instrument, anything went wrong in launch or cooling or anything like that, then this would be another case of mission over. So they actually made 2 identical modules. So there's complete redundancy. And so we get double the area of imaging that we would have got otherwise. And that was all to make sure that this instrument would be there and would be able to do all of that important work in the early days of focusing the mirror. This is what MIRI looks like, mid-infrared instrument. This is the one that needs cryogenic cooling and had its roots in the UK. So it was built by a European consortium in collaboration with NASA's Jet Propulsion Laboratory, and actually like components of it built in Rutherford, Appleton, leadership from Gillian Wright at UKATC in Edinburgh. And this was delivered to NASA over a decade ago. So this instrument was completely ready to go. It was no reason for any of the delays that meant that it took so long for us to get to this telescope. They were ready, but unfortunately, other things weren't quite there. FGS NIRISS, this was originally going to just be the guidance system. So if you know what patch of the sky you're going to look at, it's going to slew the telescope to that point and keep a very good stable pointing. It was provided by the Canadian Space Agency. So all of this shows you how collaborative an effort this has been. It's a really international effort. It's not just NASA, it's not just ESA. But they said, no, we also want to give you an amazing instrument. So it has all of the capabilities, imaging, spectroscopy, and coronagraphy. And the final one, which I'm a bit biased about, is my favorite. I talked about it last time. I'll talk about it again in this talk, is NIRSpec. And this one is particularly special. You'll notice that it's not trying to do lots of different things. It's got 3 different spectroscopy modes. And one of them in particular is one that I've been using in the past couple of years, and it's really delivering. It's beautiful. And I kind of want to point out to people how important spectroscopy is for this whole mission. The images are incredible and beautiful and pinpoint accuracy, you know, better than we had hoped for. But some of the biggest breakthroughs that we're getting from this telescope come from the spectroscopy. And that's one thing I really want to convey to people. And so there's a lot more spectra in this talk than images. So I hope that I will be taking you along and conveying to you why these are so exciting. And when it first launched, we weren't sure whether we were just going to have 5 years. It turns out we've got 25 years worth of propellant to keep it orbiting around the second Lagrange point. That means this is a multi-generational observatory. So people that are coming up through GCSEs, A-levels now, they may well be using this observatory when they're researchers in university. And that's incredible. So everything that we are finding out now, this is really just the very beginning, the very tip of the iceberg. But I would say that those original 5 years, that baseline, pretty much every astronomer would still say, yeah, it's worth it. With all of the delays, with all of the overspends, this telescope would still be worth it because there's nothing else on the horizon and there's nothing else capable of what it's doing. But thankfully we have 25 years, not 5 years. And in building such a observatory, you know, this took decades to go from original concept, design, build, and delays to the point of launch. They needed to know that they were really going to be transforming some areas of science by building this telescope. And so they identified 4 main science goals where they couldn't make the type of progress that we're making now without JWST. And in another version of this talk, I would take you through each of these science goals, and I'd give you a little update of some of the interesting things, but I think you're going to be getting some nice updates in the near future for planets. I don't work on stars, so I'm taking you all the way to the 4th science goal. So just to go through them before I move on, there's exploring planets because they are they're warm, so you can actually see them directly in the infrared. Stellar life cycle, because young stars are often enshrouded in dusty clouds and we can peer through those clouds in the infrared. And then galaxy evolution as a whole, that's kind of tied up with what I'm going to talk to you about. So I'm not telling you about galaxy evolution. But one big one, the one that I work on, the one that I want to take you to tell you some of the discoveries very quickly, is called first light. And that really is trying to find the first galaxies and stars that formed in the universe. So to set that up, I like to take a little bit of time, step back, set up the concepts, because we're using this telescope as a time machine to look back in time. And being astronomers, many of you may be very comfortable with this concept. I can't see everyone else who's in the room there. I don't know the demographics, but let me take you through the steps. Every telescope is a time machine. We may be comfortable with this. The reason is because light has a finite speed. So if it takes 1.255 seconds for light to travel from the moon to the Earth, this is how long it takes in real time in this video, then we see the moon as it was 1.255 seconds ago. So the further away something is from us, the longer it takes light to reach us, and the further back in time we see that object. So that's fine. That's every telescope. That doesn't make JWST special in any way, shape, or form. To know why we needed a huge telescope that was looking in the infrared, then we need more information. And that comes from this discovery that was made around a century ago by Hubble the man, not the telescope, that if you start to look at galaxies outside our own, by which point they figured out that they were outside our own, the further away a galaxy is, the faster it's moving away from us. So you see it's labeled a redshift, but it's been given kilometers per second. It's the measurement of speed, of how quickly something is moving away from us. So if you were to look at things close to us, they're being dominated by the gravitational force of the Milky Way. We're not going to see them moving away from us, most of them moving towards it. But the further out you get, more of them moving away. This bit is interesting. This is just a huge galaxy cluster where they're falling into this huge supermassive structure with so much gravitational potential that, you know, they are also under a stronger influence than the expansion of the universe. But if they're not dominated by that, they're moving apart from us because the universe is expanding. And so this is true. The further away that you go, faster something is moving away from us. This keeps happening the further out. And because it's moving away from us, that's shifting the light, thanks to the Doppler effect, well, the light version. And if it's moving away from us, the light kind of gets spread out and shifted to redder wavelengths. And we call that the redshift. That's where the term comes from. And if it's moving up towards us, it would be or everything gets squished up, the wavelengths become shorter, and move towards the blue part of the spectrum, and we call it blue shift. So the further away something is, the longer it takes light to reach us, so the further back in time we see it, but also the faster it's moving away from us, and so the more its light is shifted. And it is entirely possible for all of the light from the galaxy to be shifted out of what Hubble could see. So that would be incredibly distant, and it would take a long time for the light to reach us. But if it was shifted that much, it could be the brightest object in the sky, and Hubble would not see it. There's also the other factor that as it's being shifted, even if Hubble could see it, it's only seeing a very small amount of it. So we only learn a very little about those galaxies. We just see the tail end of what we could have seen. So the further back in time we go, the less information we have had until we've had this gorgeous big telescope. So there's a good question here. How far back in time could Hubble see? Or can Hubble see? Still working. And for that, I like to show this clock kind of representation where we're going back in time all the way to the beginning of the universe. And there's a few markers here to help guide. This dark blue segment here, the whole history of humankind in the universe, around 2.8 million years. We have to go back to around a third of the age of the universe to see the timing of the formation of the Earth, and close to that, the formation of the solar system, around 4.5 billion years ago. And then it's much longer ago that we estimate the formation of the Milky Way, 13.6 billion years ago. This is just one estimate. It's very hard to estimate how long ago the Milky Way started forming. People do what is called galactic archaeology, finding remnants of very old things that have been formed. So this is just one of the estimates, but still a very long time ago. And then just a little bit before that, 13.8 billion years ago, we think that the universe formed in the Big Bang. At least that's the best theory we have to explain the data. And this clock hand here is showing us how far back in time Hubble could see. So sometimes you might say, wow, Hubble couldn't see any further back than 13.4 billion years. But that's really, really good, right? It's most of the history of the universe that we could see with Hubble. So Hubble has been amazing. We've made huge progress. So that's around 400 million years after the Big Bang. But why do we care so much about that first bit? I kind of said it before, but it's worth going through again. So this is a different view of the whole history of the universe, from the Big Bang to the present day. And so with the first initial expansion, it takes some time for the universe to expand and cool enough for sort of normal matter, like neutral hydrogen, helium, to condense out of a soup of primordial, what's the word, particles. And at that point, there's dark matter, there's hydrogen, helium, smatterings of lithium and beryllium, but that's really pretty much it. There's gravity. There's the remnant light from the cosmic microwave background, but nothing else for a while. And it's somewhat boring in some sense, and we call it the dark ages, the cosmic dark ages. At that point, we would expect that there's nothing that we can see using standard light. And it takes some time before some regions, because gravity is working and because the universe wasn't completely smooth, some regions are getting denser and some are getting sparser. And it takes some time before some regions get hot enough and dense enough to ignite hydrogen fusion, and we have those first population of stars. And we think those stars are really different to the stars that we have today because they only had those primordial building blocks. So we think they're huge, maybe around 500 suns. We think that they die very quickly, and when they do, maybe as huge supernova, spewing elements like carbon, nitrogen, and oxygen into the surrounding medium. And so that's one thing I want to point out. Hubble couldn't see any further back than 13.4 billion years, so it hasn't seen back to the beginnings yet. The other thing I like to point out, only because it's something that we use to find galaxies, and I'll explain this. So I've said there's lots of neutral hydrogen back here. In the present day, if you were to go off in between the galaxies and meet a hydrogen atom, it's going to be ionized, it's going to have lost its electron. But at the beginning, it was pretty much all neutral. So it goes through this transition, which has a very fancy name of the epoch of reionization. We think it's over, pretty much done by around 1 billion years after the Big Bang. And it's just because you have now, after a certain time, you have the stars, they have energetic light that can kick away the electron from hydrogen. And we use that fact to be able to find galaxies in the distant universe. So if Hubble couldn't see any further back than this, it could see within the epoch of reionization, but NIRCam can see to within around 70 million years after the Big Bang. So we should be able to see as far back as we need to be able to find the first stars and galaxies. The question is whether we can stare for long enough, how long we'd have to sit and stare for, and whether we're lucky enough, because it's got a small field of view and these stars don't live very long. And as soon as they've died and spewed out other elements, then it's no longer pristine gas. It's no longer the first generation of stars. So actually we might have to be a little bit lucky to find them. First stars, by the way, confusingly, we call them population 3 stars. So the ones that are nearest to population 1, we've got population 2 somewhere in the middle, and then population 3 stars are the very first ones. So we're searching for the most distant galaxies in the universe. First, we have to find them. And it's a real needle in the haystack situation, because we look at a patch of sky, and one of the most wonderful images, one of my favorite ones from Hubble, was from the Hubble Ultra Deep Field, which is this patch of sky here. And it was actually a bit of a risk when they pointed Hubble at it. I think it was the director's discretionary time, had decided that they would just dedicate it to blank regions of sky. And some people have said, but you're not going to see anything. And then what pops out, but thousands, tens of thousands of galaxies. So in this patch of sky, there's around 10,000 galaxies. When we visited this patch of sky with Hubble, dedicating hundreds of hours to it in 2012 to find more distant galaxies, we found 7 likely candidates inhabiting the universe less than 600 million years after the Big Bang. So there's that clock there. And these are what they look like. A lot of the galaxies that I'm interested in are tiny blobs. They're very, very distant. We can't see much detail, very often they're marginally resolved at best. This one down here is quite interesting. It's showing 3 different images, so they're different wavelengths from short to long. And we only picked this object up in 1 image. So there just wasn't enough data for us to be able to say convincingly that this was an incredibly distant object. It was either the most distant object that Hubble could see, or it was a closer object masquerading as a high redshift galaxy. Now, what Hubble could do in hundreds of hours, JWST can do in tens of hours. And we revisited this patch of sky in October 2022. And within a week, we had gone as deep as Hubble. Obviously, it's slightly different wavelengths, so we're not looking at exactly the same thing. And this is just a small patch of sky from a large zoomable image that you could get to through this QR code or through a link that I sent to Simon. And there's beautiful details here. It's really lovely to zoom in and scroll around. This is the one I wanted to pop out of the presentation to show you, but I might just wait to the end, see if there's time. And we were taking spectroscopy just a few weeks later. Such a short period of time later, in fact, that we weren't sure if we could do anything with the images. This is part of a survey that I'm involved in. It's called JADES, the JWST Advanced Deep Extragalactic Survey, because I'm afraid that we love our tortured acronyms in astronomy. But the main point of this survey was to take imaging and spectra together, because we were 2 instrument teams. So JWST is a little bit interesting in that it's got these 4 instruments, and they found small teams of people that over the decades of building these instruments, they are scientists, they would go to these scientists and ask them different, you know, if you're making like trade-offs in the engineering or in the design, is this going to impact the science? So they had a core team of scientists that would say, no, you can't make that compromise or things like this. And in return, they got hundreds and hundreds of hours with JWST when it went up. And our survey is the NIRCam instrument team and the NIRSpec instrument team. So I joined NIRSpec in around 2016. So I wasn't one of those core people while they were building it. The instrument was already built, but we knew we were going to have around 800 hours with this telescope to take incredible spectra. So we have taken all of our data now, and we're just about to be adding more to the release, but it's not quite all of our data that's going to be made public because we get a year proprietary time. But most of our data will be updated through this same viewer. And when we're searching for high redshift galaxies, so getting back to this quest to find the most distant galaxies, it's a very simple feature that we're looking for. So it's a needle in a haystack. There's very few of them, but at least there's a simple thing to look for. And this video kind of demonstrates that. What it's showing is, these are different images at different wavelengths. Basically, for all of the different filters one could use from Hubble. So when we're just picking out a little bit of the wavelength range with Hubble and taking an image. What we show here is a spectrum of a galaxy that we're going to push further and further away from us to higher and higher redshifts. So I'll just play that on a loop for now. And what we see in the images is that we'd have a strong image there. We're often inverting them. So black is actually bright and gray is, there's nothing there. And we have this feature that disappears. We call it a dropout. Even if you were to take all of these images, add them together to try and make them more sensitive, get more depth, you wouldn't be able to see anything because the universe gets in the way. This neutral hydrogen that's in the early universe that I said we used to search for these gets in the way. And it produces this feature in the images. So we look for galaxies that disappear at short wavelengths. And if we were to take a spectrum, unless we were lucky enough to see fingerprints of different elements, what we're often looking for, I call it a cliff edge, because it's a very sharp transition. And you'll see that it's even changing here. This is as there's more and more neutral hydrogen in the universe, but we don't tend to see that bigger change. We just see the cliff edge. And using this technique, many teams with the very first images that came from in June last year were finding candidates in the early universe. And from our survey, which is a wider area than just the tiny portion I showed you before, we found hundreds of candidates in the same sort of 600 million years after the Big Bang. So we probably increased the number of candidates by tenfold within the first few months even of operations of the telescope. But until we get spectra, we don't actually know that they are distant galaxies. So I told you already there was one, we didn't have enough data to say, this is the most distant galaxy or not. And to be able to tell, we have to take spectra. And this here is the previous record holder. Again, it's a really boring, tiny smudge. But this is the most distant spectroscopically confirmed galaxy that was found with Hubble. And this little smudge here, it's a 2D representation of a cliff edge. So there's light and then there isn't light because the neutral hydrogen has got in the way and it's opaque there. So it was around redshift 11. The universe was 400 million years old by the estimate. And this spectrum here got us incredibly excited. And for most of the galaxies that we found with Hubble over a decade of working with it, we couldn't follow up in this way. We had just a handful that we confirmed and said, yes, these are in the early universe. I also want to show you another spectrum that got us really excited because I want to show you how big a difference we get with this telescope. So again, where it's black, it's bright. And these little smudges here, not much to look at, right? This is a fingerprint from hydrogen. This is a fingerprint from carbon. This was amazing to us. We were so happy to see this. Oh my goodness, there's an element other than hydrogen in this galaxy. This wasn't super, super far away, around 700–800 million years after the Big Bang. It's not the highest redshift object. But wow, we saw evidence of a different element through the fingerprints of the different elements. And this was like pretty much one of the best spectra we had. And along comes JWST. So you've seen all the beautiful images. I haven't filled up this talk with beautiful images, but the spectra are incredible. And it's thanks to this instrument, which I said was my favorite. We can take hundreds of spectra at once. So for like a decade with Hubble, we had these candidates, but we couldn't tell whether they were really in the distant universe. Thanks to this incredible array of teeny tiny shutters, each about the width of a human hair, it can let through light of individual galaxies. So each one can be open and closed independently. So if you've got a galaxy in this part of the field, you can open a few shutters here, then one down here, et cetera, and you just let through the light from the galaxies you want spectra of. It goes through to a grating or a prism and is split up. And then by the time it gets to the detector, it looks something like this. And we have spectra from hundreds of galaxies at once. So we go from 10 years of frustration, like tens of hours on telescopes, very competitive to try and even get any time to try and observe them, to in a single pointing, getting beautiful, beautiful spectra that look like this. This was our first deep pointing. So now it's flipped a little bit. This is bright in the yellow. Don't worry about what's going off on the side. Just look at the central component, or here's the 1D one. We've got this massive cliff edge. We can tell that this is in the high redshift universe. That was easy. But not only that, it's giving us fingerprints of so many different elements. So this one has nitrogen, oxygen, hydrogen, neon, calcium. So many different elements. We get to start understanding how they build up over time. Here's one at slightly higher redshifts. again, a very sharp cliff edge, easy. And all of a sudden, this thing that we were trying to do for decades, we can do with a single pointing. Now, I said we got those images in October 2022. We were at a meeting all together, the team, and we had some deep spectroscopy coming up. It was actually these spectra that we took. And we had it all planned, because normally you have to have everything planned around 6 weeks before you get your observations. But there was a problem with NearSpec. And that meant that we had to do a replan. I think we were just over a week before the observations were taken. So we had a very short window where we had new imaging from NearCam. We were going to take really deep spectra. So we found super distant galaxies that Hubble couldn't see. And we put them on our pointing. We never expected to be able to do that so early in the mission. And we confirmed 2 objects further away than Hubble could see, all thanks to the cliff edge. And this one here, this was a really nice one to see, because this was the one that we had with Hubble that didn't have enough data, and we couldn't tell. And it turns out that it was the most distant galaxy that Hubble could see. But it took us 10 years to get there, and a huge telescope to be able to tell us that. So I don't love how this looks from the press release. I prefer looking at them like this. I think it shows the cliff edge more clearly. So we have something that's very bright, and then suddenly you don't see any light from the object at that cliff edge. This is the record holder for highest redshift spectroscopically confirmed galaxy in the literature. And I would say it's a ropey spectrum, but it was enough for us to see the cliff edge, and it was better than the previous record holder, GNZ11. It was much higher quality than this. So we were happy about that. Not only that, in a single pointing, we had smashed this record 3 times. Again, took us a decade. And what else was super nice about this is, with the imaging, we could start to tell a little bit more about these objects. So they're tiny. Teeny tiny. This is what they look like in the different images at different wavelengths. So they're around 50 to 165 parsecs across, and I'll give you context for that. But around the same star formation rate as the Milky Way. So it's not quite the same as taking all of those star forming regions like Orion, Ophiuchi, or all of those beautiful star forming regions that we have in our galaxy, and squishing them into a tiny space. And by the way, how tiny a space? So to give you context, we are around 8,000 parsecs from the center of the Milky Way. If we could look at the Milky Way edge on, it's around 300 parsecs thick. But these whole galaxies are around, we had estimates around 50 to 160 parsecs. That's about the size of a few globular clusters. All of the star formation in the Milky Way jammed into teeny tiny volumes. So these things really kicked off quickly. There was nothing stopping them making stars. So these galaxies, we weren't expecting to hold this record for very long at all. This record of highest redshift, most distant spectroscopically confirmed galaxies. In fact, there was another object that was found even in the first weeks of science operations. And this one was from the same method, looking at the images and looking for objects that disappear. This was estimated to be at redshift 16 compared to redshift 13.2. But it was so luminous that none of our models could explain it. How could it be existing? And this was going to be observed on the 23rd of December. So I had submitted the paper for our high redshift galaxies. It wasn't accepted yet. And fast on our heels, we were expecting this data to come through. Were we going to be giving this record away to this other survey, SEERS? I was at home, well, with family, and we'd split into two teams because either this galaxy was at redshift 5 or redshift 16, and I was avidly scrolling and checking the archive because with this data, we would be able to see it ourselves. It was released publicly immediately or as soon as it had been sort of downlinked and processed. And checking, and nothing was appearing, and it was the holidays. And so we couldn't find out what had happened, had no idea. It turned out that for some reason, the telescope had gone into safe mode. So we didn't get the answer then. We had to wait a few more months. It was, you can actually look, if you want to look through the website to see what Webb is looking at any given time. And so we had seen that it was replanned for the end of March. And actually, the first data was released on Twitter, not in a paper as would normally happen. And seeing the spectrum, we could see very quickly what the answer was. So I would ask you, do you see a very clear cliff edge? What pops out to me straight away are these bright points, which are fingerprints from elements, not necessarily a cliff edge, right? And we can very accurately determine that these are fingerprints of oxygen and hydrogen, which places this at about redshift 5.5, not at redshift 16. So we didn't break the universe with those observations. And it showed how important it was to follow up with spectroscopy for these objects. We can find so many candidates with the imaging super quickly, potentially break the universe, saying there's too many of them. But until we get that follow-up, until we take the spectroscopy, we don't have confirmation. So there have been some others in the very distant universe that have been found and confirmed. These are two of them, another one above redshift 13, but still, this was 13.079, a little bit lower than 13.2. So we have been holding the record for much longer than I was expecting, much longer. But I would say there's been a lot of really amazing data taken recently. Watch this space. I don't expect to be holding this for much longer at all. And they were my 4 favorite spectra for quite a while, until February last year, when we got this spectrum. And this was for that previous record holder, which we called GNZ11, that tiny little smudge. Now we have beautiful fingerprints of different elements. We have a very clear cliff edge. We have an accurate redshift measurement. Actually, it's at 10.6, not at 11.1. And this has blown many astronomers' minds. We don't understand why there's so much nitrogen now. Like, how do the first stars produce all of so much nitrogen compared to carbon? We're seeing magnesium so early on in the universe. We're trying to explain how we could process hydrogen and helium to be able to produce a spectrum like this. But that's not all. Like, this spectrum has given us so much. It's shown us that it's probably harboring the most distant black hole in the universe that we have yet found. Not only that, but there are hints nearby, and they are only hints, it's not confirmed, of signatures from population 3 stars, those very first population of stars. So I won't go much more into this one, but I wanted to spend the last 5 minutes or so talking about black holes, because this has been one of the most exciting discoveries that we're seeing in the early universe. I wasn't expecting to see them or find them so easily. Some people were, but I wasn't. I think it depended what area you had come from beforehand. And again, I'm showing you spectra, and I really hope that I'm conveying some of the excitement here. So whereas I showed you some little smudges before where we saw carbon and we said we're amazed at that spectrum, we're seeing those types of features easily. They're strong and they're bright. Those things no longer excite us. The things that excite us are these weird little bumps that we see at the bottom of these emission lines. And what they are is they're telling us that there are black holes in these objects. So this is what we think might look like in the region of a black hole in a galaxy. And if we can see that, it means that the black hole has to be accreting matter at the time and then burping it out, as Becky Smether says. So what we actually see is we see the accretion disk around a black hole. That's the bright thing that we tend to see. And if we get an orientation where we can see past lots of matter that obscures our view of it, then we'll see that bright region. And we may also see a region close to it where there's lots of matter moving around very, very quickly. And that's what's causing this bump at the bottom of the emission line. So it's moving around very quickly and we can estimate the speeds, and we get estimates of 2,000 kilometers per second. So how is it that, what is it about the speed of the objects that broadens it? It comes back to this Doppler effect. If you've got things moving around in a region, some of them will be moving away from us, some of them will be moving towards us. So the ones that are moving away from us, the light from that matter is shifted to the red shifted, and broadens the line to the red wavelength, the longer wavelengths. And the things that are moving towards us, we see the light at shorter wavelengths compared to what would be classed as stationary for the object. So when we see a really broad line, that's telling us that there are things moving very, very quickly, because there's things, some of the light has been very red shifted, some of it has been very blue shifted. So 2,000 kilometers per second, giving you context to those speeds. This is a very, very fast plane, and that's traveling at less than 1 kilometer per second. We're traveling around the center of the Milky Way at 230 kilometers a second. And yet we have 2,000, 10 times more velocity in a teeny tiny space. The only thing that can do that is a black hole. So these are really robust detections, and we're only getting it really from the spectra. We couldn't tell what was happening before we got the spectra. And one really good example of this was 6 objects that caused a really big stir in the early days. I don't know if any of you saw some of the press releases, but there's giant young galaxies that can't have been formed in the amount of time of the universe. They upend our models of our universe. We can't explain them all. And what's been really interesting is seeing that there is a delay in the media compared to the science. So already by the time these press releases came out, we understood something different. And that's how fast science and understanding has been moving with JWST. So already when the press releases come out, we knew that one of them was an AGN. That means that it had a black hole at its center and it had this very broad profile. Not only that, but we're seeing more and more of them. We're getting more and more confirmed objects very similar to these. So we do not need to build large populations of stars early on to explain these objects. They are supermassive black holes where the bright accretion disk surrounding that black hole is giving us this light. And they're called little red dots, and we're finding them everywhere. And this is so exciting because we don't yet know how the supermassive black holes at the center of galaxies are formed. If we were to start off with a simple stellar remnant, we can't build them up in time to reach the masses that we see. So the most massive known black hole, around 66 billion times the mass of our sun. We have to start from heavier things. So you can imagine if you can keep finding them, getting estimates of how massive they are, we might be able to start figuring out and narrowing down the theory of how they started to form in the first place. And the data's not there yet. We're not saying this is what the progenitors are, this is how they started forming, but we actually, I think we'll be able to do it with this telescope. So that's pretty much the end of the talk. I just want to say, like, all of this is just basically two of the main results, 3 of the main results from our survey, which is a tiny patch of sky compared to other surveys that are ongoing. And we had a bit of an advantage over others in that we could plan imaging and spectroscopy all in one, whereas other teams have planned their imaging and then they're going to go in with spectroscopy, and they've started to do that. So that's why some of these spectroscopic results were a little bit slower than the imaging that was coming out early on. But so there's just so much more to discover if you think of the area that we've looked at so far. So yeah, all of that just from 2 tiny patches of sky, and it's the bare minimum of what I could tell you about. There's so much I'd love to tell you about that we've learned about high redshift galaxies, but that's a little bit of a story, I guess, of the last of a year and a half since the science operations. And I'll just take the moment to show you the image that we released, if I can share it. I have to stop sharing. Let's see. Google, there we go. So it's a really nice scrollable image where it shows you a patch of sky, the Hubble Ultra Deep Field with a small section up in this region. As you zoom in, you get more and more details. And you can just keep moving around, finding beautiful galaxies. I found some earlier, which I probably won't find again. Here we go, a lovely merger going on. There's even, you can pick different images to look at individually from the side here. And you can even, we've put in the spectra. So from that first deep pointing we took in 22, we'll be adding more in, I think it just in the next days, basically, there'll be more added. We have spectra that you can just click on and look up. So thank you so much. I'm happy to answer questions, and I hope you're not disappointed that you didn't get lots of beautiful JWST images from this talk, and I hope that some of the discoveries have been exciting for you.
Thank you very much, Emma. Round of applause. So what questions have we got that I'd like to ask Emma? We've whizzed you through to massive redshifts.
Can I just reprise on that, on the most distant galaxies you're finding? So you're saying the most distant ones you're finding are similar sizes to globular clusters we see at the moment, similar masses as well, or?
No, a little bit more massive, but that's actually a lot harder for us to estimate.
But also containing, in some cases, black holes which are several million solar masses as well.
Yeah.
Right. So how do you go on for that? Are you just going to look for more and more of them, or are you going to you were talking about the population of 3 stars? Is it then also to push a bit further back to see if you can find more evidence of those as well?
Yeah, so that's one method, is to push deeper. You actually want to also add area. So what's been interesting is that we had another deep pointing and we moved off the Hubble Ultra Deep Field, and we found a lot more interesting things, which I couldn't talk about in this talk. So this is the thing, when you're probing in such a small portion of sky, you have to be so lucky to see such a short-lived phenomenon. So it's also important to increase the area. But then what happened with GNZ11, I said there were hints that we could see population 3 stars. So that's the idea, that you don't necessarily go back to the very beginning, but you try and find pristine stars at some point wherever you can, because there'll still be pockets where there's pristine hydrogen and helium. And the idea there is that because GNZ11, there's an accreting black hole, it's actually spewing out huge outflows of gas into the surrounding medium, and sort of, if you like, scooping up all of the pristine gas in the wake, making it dense and making a perfect environment for new stars to form out of the pristine gas. So there's this idea that we can go and look around black holes, objects which have black holes, and look around in that area and see if we can find them there. So that's another strategy that is happening this year.
Hi, Emma. Can you hear me?
very quietly.
Ah,
Yeah.
Okay, I just wanted to ask,
Do you think it matters
as we
which
look further
direction you
back,
point it
will we see
to
some
find
galaxies maybe that
more of
are
the same?
primarily made up of
Will you
these
find-
population 3 stars?
You know what you might find by looking, yeah, like a whole.
So question is, if we're looking back, are we going to see whole galaxies primarily made from these population 3 stars? I mean, that's the hope. And then the question is kind of, what is a galaxy at that stage? Like, they become these fuzzier things. They're not so ordered. So yes, we'll expect to see, we won't see an individual population 3 star. If we see anything that's giving us population 3 signatures, it's going to have to be quite a lot of them for it to be bright enough. And so in a sense, yes. But they're not galaxies like we'd think of them if we're looking up at spiral galaxies or elliptical galaxies. They're just, they're more similar to globular clusters in a way, because it's a cloud of gas that has collapsed in on itself.
Thank you. And do you think this would give us any indicators for how these
Do
supermassive
the
black
questions
holes are
have to be
formed or
related
first
to
formed?
deep
Yeah,
sky?
I keep hearing 2 different things at once. I'm not sure.
I was gonna say, are there any plans to use the JWST instruments for nearer exoplanets
Yeah,
within
so this
10,
is
within 10 light years?
so those 4 science goals that I just flung in there to show you, like, that this is not an instrument, a telescope that is only looking at one thing. They're already making incredible discoveries from exoplanets, and I would expect that you'll hear about that from Lee Fletcher, who works on it. Yeah, NearSpec is being used. MIRI in particular is the most interesting for exoplanets, because you can actually see the get spectra of exoplanet atmospheres, and there what you want to look at is features from molecules, and they have longer wavelengths. So MIRI is incredibly important for looking for things like water, carbon dioxide, and other molecules in exoplanet atmospheres. So yeah, these instruments are broad ranging, and there's incredible discoveries on all axes.
Any questions from our home Zoomers? I was wondering how you're doing on your time in terms of viewing time. You said you had several hundred hours, but does that ever run out? At what point? Because at the moment, is it 10-1 on oversubscription for JWST, or is it more than that at the moment?
It's worse than that. The
It's
last
worse.
round. Yeah, the first 2 rounds weren't too bad, and then I think people saw that it was working, and then the last round was incredible. So our survey is finished, but we have priority to, like, we won't be releasing the rest of our data till basically early next year. But I think we have another 80 hours or something like that from other accepted proposals to continue doing similar science. So I guess it's like enough people from the team put something in and some things stick, and we get to continue using it.
Excellent. Any questions from the Star Vaults? Because you've been quiet so far.
Emma, do you
Oh,
think
they're not-
looking further and further back will give us more on how black holes are formed?
So it broke up a little bit there, but looking further and further back, giving more information on how these black holes are formed. Yeah, exactly. So seeing how massive they are at early times really pinpoints some of the starting points that we can have. So already GNZ11, that isn't too big. That's around 6 million solar masses, but even so, isn't super easy to build up in such a short period of time since the beginning. So it's more likely that it's starting from a heavier seed than a stellar remnant. So some examples are, say you've got a huge gas cloud that is collapsing. So the pristine hydrogen, helium collapsing down, and instead of fragmenting and producing stars, these population 3 stars, the whole cloud collapses down, and into a black hole, that would be a much heavier starting point than a single stellar remnant, where the star has had to evolve, it's ejected some of its atmosphere, etc. So this is one of the possible seeds, and we call them seeds, for how we start these black holes. So yeah, this is one of the huge questions that I think we'll actually be able to answer by doing this.
I was just thinking, are you doing the equivalent of a Hubble deep field? I mean, if you did just stare with your very small field of view at a patch of space for hundreds of hours, would you be expecting to find a modest density of these very distant primitive galaxies, or is it really that they are so scattered around you couldn't expect to find them in a random field of view?
So we went incredibly deep, as like we're deeper than the Hubble Ultra Deep Field in some filters. We could go deeper there. You could hope to find more candidates. Every time you do that, you have to spend longer on the spectroscopy to be able to confirm it. So we may be able to get more candidates, but then you also have to go through, take the spectroscopy, and you've now got something that's incredibly faint. Sometimes the imaging is going to be able to take images of things that are just too faint for the spectroscopy to handle. So in some sense, that's going to be a limiting factor. You've got two things that you've got to do: the imaging and the follow-up. I'm sure there will be people piling tons of time. There are already other patches of sky that are deeper than what we've taken, and I'm sure some people will continue to pummel into them, but just by moving, we're more likely to find more interesting things. For example, in that whole image that I showed you, as soon as we moved to a different patch of sky, so that was in the southern hemisphere, there's another patch of sky we looked at in the northern hemisphere, we found far more black holes, and we don't understand that yet. So we found fewer black holes in the distant universe from a patch of sky down there. So there's a lot of variability around, and just by putting all of our eggs into that one basket, we run into the trouble of not necessarily being able to confirm them, and we probably do miss really exciting things that we get from the area. So at the moment, just sort of like pushing to the depths of Hubble, or maybe further than the depths of Hubble, but not super deep, is the best strategy for now, probably.
Okay, all right. If there's no more questions, I'd like to thank you, Emma. You have a role, which is to bring James Webb Space Telescope out to the public and to groups like us. And your energy and your actual passion for the data. And I remember the first JWST images where the first 4 were pretty pictures and everyone was going, wow. And then the spectra was shown, and then there was an audible gasp from all the astronomers.
Yes.
Number one, working out why the image appeared to be upside down, or the spectra appeared to be upside down. But like, they say, oh, you can see that. But you bring that out. So thank you very much for inspiring so many people and giving us the update. And we'll have to have you back to see how it's going on and what you're doing with those final 80 hours and how much more time you're going to win to find out a little bit more about that distant universe. So thank you very much. Thanks, everyone.
Thank you so much.